Hello wonderful person, this is Anton, and in this video we're going to be combining the entire mass of our universe into a single object. We're going to imagine what would happen if you were to essentially take all of the matter and to kind of squeeze it all into one single piece. What would you actually get? Let's discover using Universe Sandbox and Space Engine, and welcome to What the Math. And so to start all of this exploration, we need to actually, describe a few terms or a few facts about the universe. The universe is very, very big. It's, as a matter of fact, possibly even infinite. We don't really know, and we have no means of knowing because we don't see that far into the universe. There is something called the observable universe, about which I've talked about in another video. And in this video I described to you that the actual size of the universe, basically, if you were to kind of look in this direction, and then if you were to look in this direction, and then maybe if you were to even look in this direction, you would only see at a distance of about 47 billion light years. That's essentially the limit. That's the observable limit of the universe. Now, we don't really know if there is anything else after it. Some people think, or actually most scientists today think, that there's definitely a lot more to the universe than just these 47 billion light years. Some estimates even suggested that it could be anywhere from as little as just a little bit more to huge numbers, basically 1 followed by 23 zeros, or even larger. So we don't really have any means of testing how much stuff there really is. However, we can establish the mass and the size of what we actually see, the observable universe. And in this case, the number comes up to approximately 1.46 times 10 to the power of 53 kilograms. And that just means that it's 1 followed by 53 zeros. So that's in kilograms, and we're going to try to create this object and just kind of see how big it really is and how big of a thing we can create in Universe Sandbox. And just to give you an idea of what we're actually measuring, let's take a look at our galaxy. So inside of our galaxy, if we were to actually kind of fly through it, the stuff that we see, the matter, the things like, hydrogen, helium, or even the molecules inside your body, only constitute a small part of the entire mass of our galaxy. For the most part, the total mass contains a lot of other stuff, like, for example, dark matter. We don't really know what it is, but it is there. So if we were to take a look at the entire universe, and if we were to kind of try to establish a percentage of the total mass of visible matter, you would only get about 4.8% of everything. A very large chunk of the actual mass comes from the things like, for example, dark matter, but a larger chunk also comes from dark energy. And all of them are currently not really well understood or really known at all. It's a huge mystery to us, and we still haven't really been able to explain it. But we are going to be only measuring the visible matter, essentially the actual things that you see and know in daily life. So this ordinary matter includes both the actual planets and stars, but also interstellar materials, like, for example, rogue planets or even dust that flies between stars, but also intergalactic matter. So, for example, rogue stars that might be lost in the universe, or once again, more dust. But we are totally going to be ignoring dark matter, and we're totally going to be ignoring dark energy and anything else that might not really well be understood at all. So let's just say we took all of the hydrogen, all of the helium, all of the other molecules in the universe and put it all into one single piece. So first of all, like I mentioned before, the object you'll get is about 1.46 times 10 to the power of 53 kilograms. And the reason we know the actual mass of this is based on, a few assumptions. One of them is actually the Hubble principle. And one of them is called critical density, and it's essentially the total density of observable universe based on the volume and based on the visible matter that we've been able to calculate, and also essentially based on the Hubble constant. And what you'll get here is a number that's about 0.85 times 10 to the power of minus 26 kilograms per meter cube, which is equivalent to roughly around 5 hydrogen atoms in a single cubic meter. So cubic meter is about like this big. Basically, it's a meter by meter by meter cube. And inside of this cube, on average, in our universe, you'll find around 5 hydrogen atoms. But that's, of course, including dark matter and dark energy. If you were to exclude this stuff, you would actually find even less. As a matter of fact, you would find only 4.8% of this amount, which is an even smaller number. And if you were to take this number and then multiply it by the total volume of the universe, you would get that particular value of 1.46 times 10 to the power of 53. To see how big all of this is, here is the emulation of the Milky Way galaxy with Sagittarius A star, quite visible in the middle. That's the central black hole. And our sun is somewhere, I think I had it hidden somewhere right here. There it is. I think I found it. So here's our sun. And what we're going to do now is, well, we're going to change our sun into this really, really massive object that will contain the entire mass of the visible, observable universe, but only the mass of matter, not the dark energy, not the dark matter. So here, we're going to start this by changing the value right above my head, which is the mass of the sun. And we're going to set it to kilograms just to see what it is right now. So that says 2 times 10 to the power of 30 kilograms. We're looking at something that's going to be times 10 to the power of 53. Doesn't sound like it's going to be a huge difference, but let's see what actually happens. So if I essentially, well, let's disable this so that the sun doesn't go supernova anymore. If I multiply this by 10, it will become power 31. And at this point, the sun will grow just a little bit. Then let's do power 32. Power 33, 34, 35, and as you can see, it's still kind of small. It's not really increasing in size that much. But as I keep increasing it, it will actually start changing, and I think now it has become a black hole, because at this point, it's very difficult for matter to maintain its actual structure, so it collapses into a black hole, and at times 10 to the power of 40 kilograms, it is now very, very, very large. It's about 197 astronomical units in radius, which is roughly approximately, what is it, like 6-7 times larger than the distance of Neptune to the sun. So basically this is more or bigger than our own solar system right now. But let's not stop here. Let's go to the power of 45 kilograms. So 1, 2, 3, and then 4, and lastly 5. Alright, so now you see that things have escalated pretty quickly. We're not even close to finishing, but we already have this very large, supermassive, ultramassive black hole in the middle of our own galaxy that's now going to basically kind of start eating up a lot of matter. And at this point, we are just over 10 million times smaller than the total mass of the universe. So let's not stop here. Let's go to 46, 47, and as you can see, it's now basically bigger than our own galaxy. 48, 49, 50, and I'm going to finish the total mass right here. So this is as big as you can get things in Universe Sandbox. And I changed the background here so it's a little bit easier to see, but essentially what we got here in the middle is a black hole. And this black hole is extremely, extremely large. It currently says it's about 85,000 the radius of the Milky Way galaxy, which is roughly about 4.7 billion light years. 4.7 billion. That is a huge, huge number. That's essentially 1/10 of radius of the actual observable universe. Now, this might sound like way, way too much, way more than it should be, and in reality it kind of is, because the way that things are calculated in this particular simulation is that when the mass becomes really dramatic, it changes things into black holes. And a black hole, as it grows larger and larger, decreases its density and starts expanding its so-called event horizon, which is the dark side of this black hole, at an exponential rate. And at some point, a black hole that's very, very massive becomes so tremendously large that it just kind of turns into, well, this. And so this is maybe what's happening here. So there's really no way to imagine just putting mass together. You can't, unfortunately, just put a bunch of hydrogen into a single object and expect a very large star, because unfortunately matter doesn't really behave that way. You could, however, create a very large black hole like we did here. And what you get if you combine all of this mass into one? Well, this. A black hole that's about 4.7 billion light years in radius. That is a huge black hole. Now, this may not make sense, but then think about it. A lot of things in space are literally space. It's why it's called space. So if you remove the space and you put things closer together, you'll essentially get something that's pretty big. And this is exactly what we did here. Now, for the most part, this is still very theoretical, and our black hole that we created right here is essentially based on the idea of the Schwarzschild radius. We've essentially calculated the radius of a black hole with the total mass of the universe. And that's still actually an estimate because we're not 100% sure that the mass is what I mentioned before. For the most part, assuming that what we've calculated so far is correct, this is what you would get. Now, if I were to place even the largest galaxy next to this object, it would actually be barely visible here at all. So as a matter of fact, if I were to place a galaxy right next to it, you would have to zoom in quite a lot to be able to see this. And this is how tremendously huge total mass of the universe is. Well, anyway, so that's really all we can do here until new calculations and new predictions on the total mass of the observable universe, and also until we actually understand dark matter and also dark energy a little bit better. We unfortunately can't really do anything else. So now hopefully you know what would happen if you were to put all of the mass into a single object. And I also hopefully helped you visualize what will actually happen to the universe as a one single object. But don't forget, that's only observable universe, not the total mass of the entire universe, of which we know basically nothing. Anyway, thank you for watching, and if you've enjoyed this video, don't forget to subscribe, share this video with someone who loves learning about space, and maybe even come back tomorrow to learn something else. I'll see you guys tomorrow, space out, and as always, bye bye. And if you're enjoying the videos on the channel, maybe even consider supporting me on Patreon because it does help quite a lot. Anyway, thank you for all your support, and I'll see you tomorrow.